Welcome to our first lesson on chemical equilibrium. So we're going to start by talking about what equilibrium means. So we're going to start with a simple example talking about water evaporating and condensing. So this first part says when a liquid such as water is placed in a closed container, so important that it has a lid, some way of containing the system, and heated, at some point in time, the rate of condensation equals the rate of evaporation. In other words, the rate at which the molecules leave the gas state, or the gas phase, sorry, equals the rate at which molecules leave the liquid phase. So let's just look at these diagrams underneath. And I've included on the Edmodo post a link to a video that shows the dynamic equilibrium of water, and it uses an example of a wet towel. And at first it shows the wet towel just hanging on a clothesline and how the water, eventually all evaporates out of the towel into the air and the towel becomes dry. And then the second example is a closed system, which is what we're depicting here, where the wet towel is placed in a gym bag, basically, and the zipper is zipped up, and so it's all closed inside there. And what happens is the towel stays wet because as the water evaporates off the towel and enters that little bit of air surrounding the towel, eventually that air gets saturated with moisture and that moisture starts to condense back out. So at a certain point, there's an equilibrium reached, meaning that there's, for every one molecule evaporating, another molecule is condensing. So that's kind of what this is showing here, right? So this is the condensation, leaving the gas state and going to the liquid state. And this is the evaporation, leaving the liquid state and going to the gas state. So the evaporation happens to a certain point, and then the condensation starts to begin, and they eventually equal out so that they're happening at the same rate. So we talked a little bit about this in grade 11. This is called dynamic equilibrium, because even though the number of gas molecules and the number of liquid molecules remains constant, once the liquid has reached equilibrium, the changes of state do not stop. So there's no change in the amount of gas and liquid, but they're still continually cycling through this process. The processes of evaporation and condensation are occurring. So this would be a good spot to pause my video and check out. This link doesn't work anymore, but I included a link to a video on the Edmodo post that shows the whole wet towel situation. So it's not liquid bromine going to gaseous bromine, it's the liquid water to gaseous water. So some chemical reactions are also reversible. So we're going to study the reversibility of chemical reactions and chemical equilibrium in this unit. Okay, so what exactly is a reversible reaction? Okay, so now I've included another link to a video, because obviously I can't demonstrate this for you live, what's called a blue bottle demonstration. So it's showing a process of the oxidation of glucose. And in this demonstration, an indicator is used, and the indicator is methylene blue. And this is all taking place in a basic solution, okay? So what we see happen in the video, and do watch it because it's an interesting little experiment to watch, is you see when the solution is not oxidized, so there's no oxygen present in the solution, we call that the reduced state. The solution is colorless. But when oxygen enters the system, so the oxygen is present in the air above the solution. So you'll see the person in the video shake the bottle. And when they shake the bottle, that allows oxygen to kind of dissolve into the solution. And when the oxygen enters the solution, that oxidizes the whole thing and it causes the methylene blue to change to the blue color. So methylene blue is colorless when there's no oxygen present or in the reduced state, and it's blue in the oxidized state. Okay, so this is just kind of showing the reaction. And what is interesting, and the reason we show this here, is because after the reaction turns blue, when it's allowed to settle and that oxygen diffuses back out of the solution, it changes back to colorless. And then if you shake the bottle again, it turns back to blue. And you can kind of repeat this process of from blue to colorless to blue to colorless a number of times. And so that's showing a reversible reaction, a reaction that can go in the forward direction and then again in the reverse direction. So this just says shaking the mixture oxidizes the methylene or the methylene blue, changing it from colorless to blue. And the slow reaction happens otherwise changing the oxidized methylene blue to methylene blue, which is colorless. Okay, so basically just kind of what I just explained. And watching the video is quite helpful to see this whole thing in action. All right, so let's look at another situation of a reversible reaction. And I'll just point out that not all reactions are reversible. Many reactions are not. They simply progress in the forward direction, meaning that the reactants would get all used up and form products, and then that's it. You can't go back the other way. So for example, a non-reversible reaction could be like magnesium and oxygen. So when you burn a strip of magnesium, in the presence of oxygen, you produce magnesium oxide. Once that reaction has taken place and you have your magnesium oxide, you can't then reverse that and go back to the original strip of magnesium and oxygen. So many reactions can only happen one way. So we're now focusing on some that can happen in both directions. So here's one, the formation of ammonia. So you can see nitrogen gas plus hydrogen gas produces ammonia. And you can also work the other way. The ammonia can break down into hydrogen gas and nitrogen gas. And these two processes can be happening eventually simultaneously. Once you get enough of the product built up, then you can start having that product also breaking down at the same time. So we can combine, instead of writing them as two separate equations, we can write them just one time and use a double arrow to show that the reaction is reversible. So you'll notice there's lots of arrows missing in this document. You'd always have to kind of fill them in. So a double arrow looks like this. So it's showing it's going forward and also in reverse. So what does that look like on a graph? Okay, so here's the same reaction. This is a little bit blurry, but we've got our two reactants. So here's the hydrogen and the nitrogen. Okay, so notice that their concentrations are different, right? There's a higher concentration of hydrogen at the start than there is of nitrogen. And over time, the reactant concentration decreases, right, to a certain point. Okay, which makes sense because at the beginning of the reaction, the reactants are combining and getting used up. So you start to see a decrease in those concentrations. The product, the ammonia, starts off basically non-existent before the reaction takes place, and then it gradually builds up to larger and larger concentrations. So this dotted line here is the point at which you've got enough of the product formed for that reaction to take place in both directions simultaneously, and that is the point of equilibrium. So you can see the concentrations have leveled out, which means they're no longer changing. It doesn't mean the reaction has stopped. It's still taking place, but their concentrations stay constant because the forward and reverse reactions are happening at the same time. So the notes afterwards kind of explain this. So the graph shows the concentration of NH3 is low at the start, but begins to increase. The concentrations of H2 and N2, the reactants, decrease. The concentrations of all three chemicals level off at the dashed lines. This means their concentrations are constant. They're no longer changing. The reaction appears to stop, or you might interpret those leveled off lines as the fact that the reaction's over, but it actually does not stop. The reverse reaction is happening now at the same rate as the forward reaction. Okay, so once you're past that dashed line, that's the point of equilibrium. Forward and reverse reactions are happening at the same rate. So because of that, we see that the concentrations are staying constant. So when the rate of the forward reaction equals the rate of the reverse reaction, equilibrium has occurred. At first, the rate of the forward reaction is fast, right? Because there's lots of reactants. So as those reactants get used up, it starts to slow as the concentration of the reactants goes down. As soon as NH3 is present, so as soon as you have enough of the product, then the reverse reaction will start. And as that concentration of NH3 increases, the rate of the reverse reaction will increase. So eventually the rate of the forward reaction equals the rate of the reverse reaction, and equilibrium has occurred. So I also included a link to a video that shows reversible reactions. So this would be a good time to pause this video and check that one out. It's not this link, it's a different link. Okay, so how do we interpret these graphs? So there's a concentration versus time. So this is just showing in general, the reactants decrease, right? The concentration decreases first at a fast, like a steep slope, then the slope starts to level off, whereas the products start basically at zero and increase first at a fast rate and then slows. And at this dashed line, this is the point of equilibrium. The reaction continues past that dashed line, but the concentrations of the reactants and products are no longer changing. Okay, so they don't have to be the same concentration. They just have to have a constant concentration, which means that they've reached equilibrium. Okay, whoops. On this graph, you can see it's rate versus time. Okay, so the rates are kind of converging here. We've got the fast rates slowing down for the reactants, whereas the product, the rate of the production of the products starts also fast and slows until they converge at the same rate. Okay, so the rate of both reactants and products past this dashed line is the same. So just another way to look at the process. Okay, let's finish up this little bit about kind of the overall idea of reversible reactions and equilibrium, and then we'll get into some calculations. So concentration versus time, this is just explaining the graphs kind of as I just did. The horizontal line shows that after equilibrium has been reached, the concentration of the reactants and products do not change. Okay, and the reaction rate versus time, the second graph, once equilibrium has been reached, the rate of the forward reaction equals the rate of the, I don't know, that line doesn't need to be there, of the reverse reaction. So the forward reaction produces products, and in the reverse reactions, products are being changed back into reactants. So you have this situation that is occurring. Both things are happening simultaneously at an equal rate. So what do we need for this equilibrium to happen? Well, first, a closed system. You can't be allowing anything to escape, right? Or else it's no longer present to change back into the reactants. Okay, so a closed system, so the products can't escape. It must be a reversible reaction. You can't reach equilibrium if the reaction can only happen in one direction. The temperature must stay constant. And the rate of the forward reaction equals the rate of the reverse. All right, so let's move on to what we can do with this, some calculations. So that's kind of the theory behind reversible reactions and dynamic equilibrium. Let's look at some calculations. So this is just reviewing a little bit. Most reactions reach a state of equilibrium where the rate of the reverse reaction equals the rate of the forward reaction. This means that the reactants are not completely used up in the reaction. And because not all of the reactants are changed into products, the reaction produces less products than the balanced equation would predict. So let's look at this law and what sort of formula we can get out of it. So the law of chemical equilibrium states that at a given temperature, a chemical reaction reaches a state where the ratio of the products, or sorry, that should be product and reactant concentrations has a constant value. So the formula that we're going to come up with here is to calculate a constant, and we call that constant KEQ. Okay, so we do that by comparing the concentrations of the products to that of the reactants. So if we were to have a balanced equation in this format, right? So here are reactants, here are products. The lowercase letters are the coefficients. We can derive the KEQ, the constant value. Okay, so this is what this is. It's a constant by taking the concentration of the products raised to their coefficients. Okay, so the product of those divided by the product of the concentrations of the reactants raised to their coefficients. So the product concentrations are divided by the reactant concentrations, and they are raised to the same power as their coefficients from the balanced chemical equation. So the concentrations of A, B, C, and D are the concentrations at equilibrium. Okay, so that's why you see this EQ here. This is the constant. We're comparing these concentrations at equilibrium. KEQ is only constant for a reaction at a constant temperature. So the KEQ will change if the temperature changes. Okay, because then that is going to change the rate of the reaction. So let's first start with homogeneous equilibria. So homogeneous just refers to this, means the same. So in this case, we're talking about reactants and products are all being in the same state. Okay, so here's an example of a reaction. We've looked at this reaction already. Nitrogen gas plus hydrogen gas produces ammonia gas. So I'm just going to add in my double arrow here. Okay, so we're going to write this out in an equilibrium constant expression. Okay, so that's really what this is that we're doing. We're just going to sort of write it out. So what I do is I write K, excuse me, EQ, and I'm going to start with my products. Okay, so I put the concentration of NH3, and I'm going to raise that to the power of 2 because of the coefficient, because I've got 2 molecules of that. So I'm multiplying the concentration of an NH3 by itself, right? 2 times. Then I'm going to do my reactants. Okay, there's only 1 molecule of nitrogen gas, so I don't need an exponent. There's no coefficient, but there's 3 hydrogens. Okay, so I need to multiply that 3 times. So I'm going to raise it to the power of 3. Okay, so and that's all we can do at this point. We have no values for what these concentrations actually are. So we just write it as an expression at this point. So for the second example, again, a reversible reaction. You can only do these if it's a reversible reaction and it's at equilibrium. So we put our product on top. That's the NO2. There's 2 molecules. Okay, divided by the N2O4. And there's just 1. So it just stays like that. Okay, so what about a heterogeneous equilibria? So all that means is the reactants and the products are in more than one physical state. So they could be solid, liquid, or gas. So really, because we're talking about concentrations here, the only state of matter that we're going to be able to deal with the concentration here is the gas state. Pure liquid or solid reactants or products have constant concentrations at a given temperature. So we don't even include them in the expression, okay, because their concentrations are constant. So it's really only the gas state and aqueous solutions. Aqueous solutions can have concentration, right, depending how much solid is dissolved in liquid or in water. But we're not going to look at those quite yet. But that is another type of state that could be included. So let's look at this one here. Again, I'll add my arrow. So you can see our reactant is solid. We have a solid product and then 2 gas products. So we're not going to include this reactant or this product because their concentrations are constant. They don't need to be included. So therefore, all I can really write here is CO2, concentration of CO2. There's no coefficient, multiplied by the concentration of H2O. Also no coefficient, so no exponent. This is not going to make, there's nothing to divide by here, so that's all there is for that one. Oops. Okay, here's another one where we've got some solids involved. Okay, so we've got a solid reactant and a solid product, so I'm going to leave those out. So I'll simply have my product of CO2 raised to the power of 2 divided by the concentration of carbon monoxide to the power of 2. So this is just a few more practice problems. You can kind of, I'll do a, like, I'll maybe just do a couple more and then I'll post the remaining ones tomorrow when I post the answer key for the worksheet. So I'll do just a homogeneous one. So this would be KEQ equals the concentration of NO to the power of 2 over the concentration of N2 times O2. Now I'm going to skip down to this one here because it's a little different and show you. We've got liquid, liquid, gas. So you're not going to include the liquids. So now you don't write this as a fraction. If there is only one concentration involved, you would just simply write it like this. All right, one more thing to show you, and that is how to plug in values once you have the expression. So here is a reversible reaction. Okay, and we're given the concentrations for both reactants and the products. So you want to start by writing the expression. Okay, and then it's just a matter of plugging in the values. So for H2, and then, or sorry, HI, H2 is 0.046, and I2 is 0.0029. Okay, so all you would do is calculate that, and that just tells you that the KEQ, the constant, equilibrium constant, is 66.94. Okay, we'll do one more. This one is pretty straightforward because there's only one gas included. So the KEQ is simply equal to the concentration of iodine gas, I should say. So that means that it's just this value here. All right. You can work on worksheet 1, which has calculations similar to these and the ones prior.